Hello. Today we are going to see ultraviolet spectroscopy part 2. Previously we have covered the basics of UV spectroscopy. Today we are going to concentrate on Woodward-Pfizer rules for calculation of lambda max in nanometer for dynes and dinones. First of all, what is the meaning of dyne? Dyne is a system containing two double bonds, but they should be conjugated. To be UV active, these two should be one after other. That is called as a conjugation. So this is dyne. According to them, the basic lambda max value for dyne is 215 nanometer. When any double bond is in further conjugation of this dyne system, additional double bond in conjugation, for every double bond 30 nanometers are added in it. So in this it will be 215 plus 30. Suppose there is a substituent over here. This is methyl. For each alkyl substituent, I am just now concentrating only on alkyl substituent. 5 nanometers are added. This is for an open chain compound. For a cyclic compound, this one is a dyne, cyclic dyne. This type of system is called as a homoannular dyne. For a homoannular dyne, (39 nanometers are added. This is homoannular. This is also homoannular. But if you look at this structure, in this system, two double bonds are in two different rings. This one is a heteroannular dyne. For heteroannular dynes, 39 nanometers are not added. If you see a system, a bond outside a ring is called as an exo bond. If there is a extra bond outside a ring like this, or for this is a bond which is outside this ring, or this is a bond outside this ring, for each exo bond 5 nanometers are added. So these are the simplest values we have to remember. These people have worked so hard that even today the observed values of these dynes and enones found by running the UV spectrum and by calculating the values, they are matching exactly equal. Now we'll take one example. or we'll take two isomeric compounds. And we'll calculate their lambda max values according to Woodward and Pfizer. These two we will calculate simultaneously. What you can see in this, is it a diene? Yes, it is diene because there are two double bonds which are conjugated. So what is the basic lambda max value? 215. In this also these two double bonds are there, but they are also conjugated. So we will write the basic lambda max value as 215. Both compounds are isomeric by molecular formula. What you can see next? In this one, these two double bonds are in the same ring. So we have to add 39 nanometers. In this one, these two double bonds are in two different rings, so no addition of 39 nanometers. In this one, this is one exo double bond which is outside this ring, so 5 nanometers are added. In this one, for this ring, this is one exo double bond, and for this ring, this is one exo double bond. So total is 5 plus 5, 10 nanometers are added. Now the next one is, there is no extra double bond in this one as well as in this one. So we cannot add additional 30 nanometers. Now the substituent part. This is the system under consideration. This is the system under consideration. This is one carbon substituent. This is second carbon substituent. This is third carbon substituent. This is fourth carbon substituent. This is fifth carbon substituent. This is sixth carbon substituent. So 6 into 5, 30. So 30 nanometers are due to alkyl substituent. Now we'll calculate substituents in this system. Carbon substituent. This is 1, this is 2, this is 3, this is 4, this is 5. So there are 5 substituents, 25 nanometers are added, nothing else. No extra double bond, so total becomes 284 nanometer in this one and 255 nanometers in this one. So even by using this rule, you can differentiate between two different compounds, two isomeric compounds. Suppose now there is one extra double bond in this. The value on conjugation, that is pi to pi star conjugation, 30 is added, it becomes 285. Now this is near to this one, but homoannular system plus homoannular system. See the effect of only extra one double bond. The value has become 324. Here it is 284. See the effect of homoannular diene. and how you can distinguish between the isomers, what is the use. It can predict the structure, it can compare the structures with the data over there, and you can get idea about the structures using Woodward-Pfizer rule. This is about dynes. Now we will continue with enones now. What is meaning of enones? In is double bond, on is ketone. This one is a enone system. Calculation of lambda max in nanometer for enones. Rules for that. Again, the basic value is same. If there is an additional double bond, 30 nanometers have to be added. For alkyl substituents, there is a difference in that. This is alpha position, this is beta position, this is gamma position, this is delta position, and so on. For alpha position, 10 nanometers are added. For beta, 12 nanometers have added. And for gamma, 18 nanometers are added. This is the difference. And I am again concentrating only on alkyl substituents. Homoannular dyne system 39, same. Exo bond 5 nanometers, same. Now we'll take one example and calculate the value of the enone. Before that, I have to tell you, if this R is H, the value is 207 nanometer for R is equal to H. And if the ring is 5-membered, value is 202 nanometers. Please remember this. Now I am going to take one example of enone. Simple enone. First I'll take open chain. Is this enone? Yes. Double bond carbonyl in conjugation. So 215. Is there any double bond in conjugation? Yes, one extra double bond is in conjugation. So 30. R is mentioned? No. So we are not going to add anything about that R. Now about alkyl substituent. Is there any substituent here? No. So alpha is 0. There is substituent at beta. Beta is 12 nanometer. No substituent at gamma, delta. After gamma, all are having value of 18 nanometer. So the value of this system is 257 nanometer. And then now we'll take one cyclic enone. Now to start with en or enone, we have to always start with enone part. This one is a enone, so base is 16, 215 nanometer. Two double bonds are in conjugation, so 13 to 2, 60 nanometer. This is homoannular dyne, so 30 is to be added. Exo double bond, can you see here any exo double bond? Just look at this system. This double bond is exo with it. So 5. For this system, this one is exo. Another 5. So 10 nanometers have to be added. Now the substituents. On alpha there is no substituent. On beta there is a substituent. So 12. On gamma there is one substituent. 18 is added. This one is a conjugated system. We should not take any substituent on this. Hydrogens are not substituent. But on this double bond, this one is a common alkyl substituent, but its value is to be added, and that is going above delta. So total is this. So 363 nanometer. This is how the values of enones are calculated, and this is the application of Woodward-Pfizer rules. Here itself you can see that pi to pi star transitions increases lambda max value. This is due to lesser energy of transition, higher the lambda max value, higher the wavelength. This is the use of Woodward and Pfizer rule. These were the great people. At that time, they did so many calculations and found exact rules to calculate the value, which is matching with the observed values. Thank you.